Hey there, it's Shannon Magic Myers, and today we're going to look at circular motion. So let's say you have some particle that's moving on a circular path. So this circle is the path. The particle, I don't know, could be this guy here. Let's say you've got a particle and the particle is moving on this path. Okay, and so B is the radius, all right, the radius of the circle, and the circular path is described by using the vector r at t is equal to b times cosine omega t times I plus b times sine at omega t times j. So this is the path of our particle right here. So I'll just write that in. Hopefully it's visible. So yes, r at time t is b times cosine omega t times I plus b times sine omega t times the vector j. Groovy? All right. And so now let's just check out a couple of things. Actually, one of my students had asked about a problem about a car on the road and wanted some more explanation about it. So we'll do some preparatory work so that we can understand that problem, which will be on a different video. Groovy? All right. So now let's take a look at what we have going on for the velocity vector in general. All right, so let's find the velocity vector. That'll be our first task. We'll find the velocity vector, and we're going to show that it is orthogonal to r. And r is in terms of t. Okay, so let's check it out. Well, what is the velocity vector? Awesome, we're going to differentiate r at t. So here's our r at t. And we just need to differentiate this with respect to time, right? To get r prime at t, which we can call v for velocity, right? So when we apply the chain rule, remember that for the first part, the derivative of the cosine of something is negative the sine of something, and we've got a linear function in the angle, so omega will be a multiplier as well. So at the end of the day, we will get negative b times omega times sine at omega t times I. Sorry, that negative's a bit low. And then plus b times omega times cosine omega t j. Good so far? Awesome. Now, that's the velocity vector, so that's the first part. And I mean, if you wanted, we could factor out an omega times b if you'd like. I'll just leave it as is. The first part of our task is done. We found the velocity vector. The velocity vector is this one here. Cool, cool? All right, so And remember that this is also v for velocity at t. It's that first derivative of r at t. So now we want to show that it's orthogonal to r at t. Well, how do we figure that out? We would find the dot product between them. So r at t dot v at t will equal to, well, what will we get for our dot product? How do we find that? Good. We just, we multiply the corresponding components, right? So if you'd like, we can certainly, sometimes it's easier to see in component form. Let me drag this over here so I have more space. So here you would have the first vector, r at t, remember, was in the pink. So we would have the first component is b times cosine omega t. And the second component is b times sine omega t. For our velocity vector, the first component is negative b omega sine at omega t. And then the second component was b omega cosine omega t. And then completing that dot product, what will happen, you're going to get negative b squared, because b times negative b, omega times cosine omega t sine omega t, plus b squared times omega sine omega t cosine omega t. But don't those zero out, right? Because we can commute the cosine omega t and sine omega t. So we'll end up with 0, right? And because the dot product is 0, that means that the velocity vector is orthogonal to r at t. Cool, cool. So our second portion it being, of course, the velocity vector. Is orthogonal. Good so far? Right? So, very good. That is our first job. Now, so basically, any velocity vector that you're going to make is going to be, remember, is going to be orthogonal to our position vector, r. So now, why don't we take a look at the speed. What would the speed of this particle be? All right. So, in general, right, if we find the speed of the particle, well, remember that speed is the what? Beautiful. Speed is the magnitude of the velocity vector. So in order to find that, we will find the magnitude of our velocity vector, which is the magnitude, I'll put it in component form, of our vector negative b times omega sine omega t, and then b times omega cosine at omega t, and then that will be equal to the square root of the sum of the squares, right? So we'll get b squared omega squared sine squared omega t plus b squared omega squared cosine squared at omega t. But we can factor out a b squared omega squared within that radical. And do you see we'll have sine squared omega t plus cosine squared omega t. Which is the square root of b squared times omega squared times 1, because recall that this is a trig identity. All right, so we will have our speed is b times omega. And b and omega are constants, and so the absolute value of our constant will just be the positive. So we're not going to go in a negative speed. All right. So this is the solution for finding the speed of the particle. Okay, so what have we found so far? We have found that our velocity vectors are always going to be orthogonal to r at t. So here, if we have some point in time here, right, then we would have a velocity vector like this. That would be some velocity vector here. And notice it's perpendicular to where r is at a given time. Actually, I'll draw that in a different color. This would be our velocity vector v. Cool, cool. This would be another velocity vector v. Actually, call that first one v1. You could call this v2. However you want to think about it. Those are all perpendicular to r, which is the circle itself. That's that path. Okay. And so now we know that the radius has to do with the calculation of the speed, the radius and the coefficient to the time, the omega, the angular speed. So the product of the omega, which is the constant angular velocity, and the radius b is the speed. Good so far? All right, so now let's take a look at, and that of course is the magnitude of these velocity vectors. So now let's take a look at the acceleration vector. Let's check it out. So here the acceleration vector is going to be the derivative of the velocity vector, right? So recall that our velocity vector that we found was equal to negative b times omega sine at omega t times I plus b times omega cosine at omega t times j. And so differentiating with respect to t, we can find the acceleration vector, right? And so what will we have now? This will be negative b omega squared cosine at omega t times I, and then minus b omega squared sine at omega t times j. I just differentiated with respect to t, and considering that b and omega are constant, right? So now let's see, what we would get. So I want to write this in terms of r at t. So here, if we were to factor a little bit, and remember what was r at t? B cosine omega t plus b sine omega t. So if we factored out a negative omega squared, we would have b cosine omega t times I plus b sine omega t times j. And remember that that was our original r, right? And so the acceleration vector at time t will be negative omega squared times r at t, right? Times r at t. Well, what is that going to tell us about the direction, right? So the acceleration, if you're considering, the acceleration of some point on the circle, is going to be negative omega squared. Well, what does that tell us? Beautiful. That tells us that our acceleration vector is going to be pointed towards what? Good, towards the origin, right? So the acceleration vector will always be pointed towards the origin. Sorry. And so acceleration vector, right? They're always going to point towards the origin or the center of the circle. Cool. All right. So that is that. And so we found the acceleration vector. And so now let's talk about the magnitude of the acceleration vector, and then we'll be done. Well, about the circular motion in general. So if we find the magnitude well, what would we be working with? The acceleration vector was a at t equals negative omega squared times r at t. Well, in this case, I'm going to write r at t out. So we have b cosine omega t I plus b times sine omega t times j. And so the magnitude of a at t will end up being the absolute value of a negative omega squared times the square root of b squared cosine squared omega t plus b squared sine omega t. And sorry, the sine is squared. So this will end up being omega squared times the square root of b squared times the quantity cosine squared omega t plus sine squared omega t. But what is that trig identity? Beautiful, that's just 1. So you're going to get the square root of b squared times 1, which is omega squared times b, which is the radius of the circle, right? So this all connects together. And so what ends up happening, all right, so the speed of the particle, isn't b going to be constant, right? So as your angular velocity increases, your speed increases, right? So we found that out. We've also found that the position vector at time t and the velocity vector at time t are perpendicular, right? And we've also found out that our acceleration vector is always pointed towards the origin or the center of our circle. And so now that's our first part of our circular motion. And go ahead and look for circular motion part 2 if you want to see a particular example. All right. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, please subscribe and tell your friends. Bye.